So thank you for everybody staying this late and wanting to join this session. We're going to have 5 members in the panel coming from different companies. And my name is Sergis Mushal. I'm a director of research with Gartner. I cover the processors and the data center technologies for the semiconductor team at Gartner. Today we're going to have representatives from ARM, from Intel, from AMD, from Microsoft from an end user perspective, from IBM from an open server perspective, and also from Applied Micro, which is the first ARM vendor providing the ARM processors for the servers. With that said, we're going to have Jeff Underhill, Director of Server Program with ARM, Gaurav Singh, VP of Engineering from Applied Micro, Carl Freund, VP of Server Marketing at AMD, Nidhi Chappell from Intel as a Product Line Manager, Mark Shaw, Director of Hardware Engineering from Microsoft, and Norman James, Senior Technical Staff Member at IBM. We're going to be doing a 5-minute quick pitch, and from there the panel is open and we're going to have discussions. Please keep your questions coming. This is all about your Q&A and it's about engagement and discussions. With that said, let us go ahead and in 1 minute we're going to be able to proceed with the first presentation. Okay, to start the event, since we have only one lady on the panel, we will start with the ladies first, and we'll take it from there. Nidhi, as I mentioned, is the product line manager for Intel, and she will be presenting her perspective from Intel side, and we will proceed with the rest of the team from there.
Good evening, everyone. Yes, I'm the only female on the panel. Hopefully next year onwards we'll start to change that, but for now let's go with that one. My name is Nidhi Chappell. I'm actually the product line manager within data center team at Intel. So I manage all of our server SoC product lines, the Atom-based product lines and the Xeon D, which we just announced recently, which is our Xeon Core product lines. Today I'm actually going to be talking a little bit around what is our overall strategy. I think we've had a few, we had Regine as the keynote speaker before, we had Stavros talk yesterday and a few things, so you'll see similar themes in my conversations, some of the similar themes that we have talked about in general in other conferences too. And then I'll talk a little bit about the emerging hyperscale market, what is the Intel roadmap there, and then open up to questionnaires after that. So let's start off with something that we talked, Regine, for those who attended her keynote, she talked about this before, and I think a lot of audiences and lots of key customers have talked about this. Kushegra pointed out, the speaker from Huawei pointed this out, that with the emergence of digital services economy, our current data center does have limitations. We've talked about, and this is, again, I'm not bringing anything new here, I feel like, but I do want to tie this up, that we have recognized that there is limitations when you start to become, IT becomes the cost, you actually do start to look at optimizing the cost, reducing the cost by having very specific hardware that is optimized for your application, general purpose performance computing, which Intel has pioneered in the last few years, and actually many years, that does seem to have problems in that area. We recognize that The other area we talked about before, and you've seen the theme happen many, many times, people call it STI, STN, STS, but this, being able to manage your storage, your network, your compute more cohesively. Today they are siloed resources, we're not managing them properly. Okay, that's been the general theme here, and the resulting impact of all of this, which you hear it from end customers, you hear it many, many times, is that the applications that we are delivering, you limit how quickly you can deploy a new application, how quickly you're able to enable new services. So we at Intel do realize that the legacy data center, the traditional data centers, if you will call, optimized for certain type of workloads, may not work in certain other kind of workloads. So, a change has to happen, and I think we'll be first ones to actually say that it is time to disrupt that data center. So, again, you probably heard this in other conversations. We had this yesterday and today. We have 3 different pillars where we talk about. We talk about custom silicon customization, which just a quick overview means that we are opening up to actually moving away from everything under this general purpose, everything under the general purpose market, to having more customized solutions. We showed before a video with Facebook where we did very strong collaborations with Facebook to make sure the workload that they have, we could actually provide a customized solution to it. And you saw that from Regine too, within 1 year we've gone from 15 custom solutions to 35. So there is a theme around that. That's the box under silicon customization. Then the next theme we talk about, again, is breaking that silo, breaking that box of, compute only, storage only, networking only, to having a more disaggregation, but still a logical aggregation at the top, so you are able to deliver the best applications. And the end goal of all of this is making sure that the digital services economy, the hyperscale workloads that are sitting behind that, are able to provide the quick service that an end customer has come to expect in the economy today. I'm not going to talk a lot about breaking the box, and I'm not going to talk about how we are doing the optimized service delivery, because Regina actually talked about it a little bit. I don't think I'll bring anything new to the conversation. What I thought was, for this particular panel, I wanted to focus a little bit upon silicon customization and talk about how our roadmap, and happy to go into more details later, would actually provide for the needs of the emerging workloads. So the first thing I wanted to do is start by looking at the workloads. As I mentioned before, our theme has always been optimized for majority of workloads on our general purpose SKU stack. We want to go, and there is benefit to it. You get benefits of economies of scale. But then, as we mentioned before, there are markets. We had a Xeon Phi product line. You have the high performance HPC, which requires density, but really high performance FP cores. You have the Xeon Phi product line that we announced. Then on the other end, we also had the microserver market, which will actually be delivering the 3rd generation next year. But that we started off with the Atom product line, saying, again, we recognize that there is a market for low power, high density, and we started to look at Atom product line. And then on top of that, we've actually also opened ourselves up to custom solutions, where we are talking to some key customers, where we are talking about taking their particular IP and optimizing it and building it into our own solution set. So this is all in the vein of being open as a silicon company to optimizing, being able to deliver the workload-specific solution for each and every customer. Okay, going back to that, I think the inherent thing that we bring to the table is a deep understanding of workloads. For a very generic crowd here, I wanted to show, if you were to put all the workloads on 2-dimensional, compute and I/O intensive, the conversation that I want to focus on today is what I call the hyperscale workloads, and the lower end of that is dedicated hosting, web surfing, memcached. Regina actually talked about some of them before too, but that's the place where we started to put our emphasis on microserver. We realized we started off with Atom product line, with Centiton, And then we have the Aviton C2000. We've been seeing a lot of success there. And next year, we will actually be launching our Xeon D product line, which is actually our Xeon Core and SoC. Three key requirements I see for this market, and we can get into more details in a quick Q&A, but performance, power, efficiency, and being able to deliver, being able to deliver a solution to market. So just wanted to quickly hit those points. And performance, I kind of went back to, how do I tie up the performance? Because Intel has been associated with bringing a CAGR of performance and delivering to it generation over generation. And I kind of brought this theme back to which, I know it's an older paper, but it just still stuck with me, is that, whether we agree with the Wimpy core versus Brahmi core, or all of that discussion, I don't want to get into that. The key theme still is to actually be successful for workloads, you actually do have to deliver single core performance. You actually have to have decently good performance, otherwise you are stuck behind Amdahl's law. So, there's always that element of it. So, performance-wise, as I look at our roadmap, and I manage all of our product lines, I feel pretty good that the roadmap we have will deliver the performance we are talking about. Then on the top there, I talk about the manufacturing process, and that is where some of the unique benefits that Intel brings to the table, along with performance, we have kept a very strong, we've delivered a very strong manufacturing process. We've talked about 14 nanometer being delivered to the product. I cannot talk about it in a lot of detail on the server side of things, but if I was to use the proxy from client side of things, I just saw a quote from Forbes there, which was, it is a game changer. What it means is that we'll be able to provide much better power efficiency, performance per watt. What it enables is lower leakage. You can actually have much higher density compute in a small form factor. So again, it goes back to the promise that we bring together. And then the last example that I wanted to bring here was, just pure execution, being able to deliver consistently to the market. And even in the emerging SoC microserver space, with Xeon D, will actually next year be on our third generation of 64-bit. And actually it's pretty exciting, because the way I look at it is, whether there is a lot of adoption for SoCs in the server space or not, what we do end up seeing is, if there is adoption, a lot of that is actually happening on IA. And not only is it happening in the server space, but it is actually allowing us to get into markets like low-end storage and comm side, where Intel traditionally didn't have a very strong presence. So I look at it as the server SoCs that we started developing for microserver spaces, allowing us to grow into markets like comms and storage. So,
I thought it was 5 minutes.
Yep. So this is actually my last slide. So thank you for the check on that. The key messages I wanted to say is, be a disruptive force in the data center. We've actually talked about this. What Intel brings to the table here is server performance, on leading edge process, and having the biggest software ecosystem to go with it. That's all I have. Thank you.
Next, we'll invite Arm. Jeff, if you could join us up here. And we're going to give Arm also in light of that 10 minutes.
Wait, how long do I get? This is slide 1 of 300. You shouldn't have let me up here, I'm telling you. So my name is Jeff Underhill. I'm a director of server programs at Arm. And I've been with Arm for about 5 years now. Prior to that, I was in the x86 space and saw the SoC movement kind of starting to happen. ARM's foundation, or DNA, is built on low power. The ARM partnership has been delivering SoCs to the market for over 20 years at this point. So that's fundamentally what ARM and the partners do. So just a little bit of background. We're a little different to traditional silicon partners in that we don't actually make chips, we don't make systems, we develop intellectual properties, and we're the stewards of the ARM architecture, and then we license that to other innovative companies that can use as much or as little of that as they wish to put compelling solutions together. So it makes it with their own IP, with third-party IP, etc. As far as delivering, so to date, since 1993, ARM and the partners have delivered 50 billion chips to market. And 50 billion, big number, great. What's really interesting, I think, is if you look at that curve, 10 billion of those occurred last year. In the most recent earnings, we talked about 3 billion in a quarter. So there's some pretty significant shipments of the ARM architecture occurring today. We're looking to take that into the data center and throughout network infrastructure. So a rough breakdown of where those ship today, it's about 20% into embedded, 16% into enterprise and network and storage applications, 58% the bulk goes into mobile, and then some into home. I wouldn't mind betting that everybody in this room has interacted with multiple ARM-powered devices today. The SoC model and the low power DNA is why we can all have fairly performant cell phones in our pockets. So what's happening with servers and network infrastructure? Servers have historically been very general purpose. Networking equipment was very kind of fixed function. And we're starting to see where servers need to become more workload optimized, especially in these scale-out worlds where you have a workload that you're running many instances of. And then the networking guys have seen some of the flexibility and scalability servers have with virtualization, and they realize that in order to deploy new services to market quickly and to meet the future demands of data, they have to instill more flexibility into their silicon, their designs, their infrastructure as well. So there's this kind of beautiful convergence happening where everybody wants software defined, and I just say X here because there's so many different software defined things. But fundamentally, everybody's after an accelerated pace of innovation, more flexibility, more efficiency, and the ability to deploy virtualized solutions quickly. And that's where the SoC model is a perfect fit for this, combining best-of-breed intellectual property from companies like ARM with partners like AMD, Broadcom, Cavium, etc., into unique and compelling solutions. So today, we're already at the point we have a 64-bit architecture. We call it ARM v8. It exists in multiple pieces of silicon today. And I'm going to point out just a couple of key features with this. When we decided to develop the 64-bit architecture, we didn't just take our 32-bit architecture and extend all the registers and make them 64-bit. We literally went back to the drawing board and architected a 64-bit execution state from the ground up. So this allowed us to do this in line with new programming methodologies like C11, C++11, new JITted dynamically typed codes. So it's a very efficient instruction set to decode with a fixed length instruction encoding. And we have primitives for load, acquire, store, release. That's very good for highly threaded environments. So the 64-bit architecture is going to be super efficient. This is a block diagram. I'm not going to go into details. What I really want to point out here is this unique blend of ARM IP and partner IP. And this is where the magic happens, when you kind of empower innovative companies with the freedom to innovate, to mix these combinations of IP together into these differentiated workload optimized solutions. And we'll hear from a couple of ARM partners about that later on today. So in summary, driven by a real strong desire to optimize for TCO, and TCO is king at scale. The data center shift to scale-out type workloads and the SoC model is clearly already underway. Highly integrated SoCs have already dominated a lot of other areas where power and size is a concern. That's come into the server space now. The ARM business model is a collaborative one, working with a network of partners to bring best-of-breed solutions. And our belief is that if you empower the world's best and brightest with some key ingredients and then give them the freedom to innovate, great things happen. And that's what we're starting to see here with the emergence of ARM-based SoCs for the server and network infrastructure. Thank you.
Next, I would like to invite Norman. Norman is with IBM and Open Power. This way we'll have x86, ARM, and Open Power.
I'm Norm James. I'm representing Open Power today from IBM. If you're not familiar with Open Power, IBM recently opened up the power architecture, and there's now a consortium with about 50+ members that are trying to use power architecture to innovate and power IP. So IBM opened up the architecture, opened up the firmware and the IP so others can innovate using that architecture. And my job today is to go out and teach partners how to use Power Architecture to do system design, and how to write firmware and to use the Power Architecture to do their innovations. So instead of talking specifically about the Power Architecture and Open Power, I was going to just hit a few points on where I think the future of computing is going based on what we've seen. So we've heard this theme a little bit throughout this conference where the TCO is king, and it's getting more difficult to improve TCO with newer technologies. So there has to be other ways to improve the TCO, not just by going to the next technology. So I'm going to hit a few points on where I think we can improve TCO without just relying on the chip or the CPU architecture or going into new technologies. So the first point would be quality of service monitoring. In the cloud environment, it's important to pack as many virtual machines on a system as possible. So through quality of service monitoring and automated throttling, that'll allow you to do that. So you get better utilization of the system. That's totally independent of the CPU architecture. External coherently attached devices like accelerators, flash controllers. These they leverage the community to create innovations. It's similar to the open source software model. It's more of an open hardware model. So if you have coherent attached buses, you can create your own IP and innovate on a very low latency, non-IO access model. Another important area is DDR alternatives for memory attachment. As we pack more cores onto the chips, it's getting harder and harder to feed it with memory bandwidth. And DDR is pretty heavyweight with respect to pins, so you're getting larger and larger modules to support that. So we do need an alternative for some high-speed serial interface to the memory. There are some alternatives out there that are being discussed, but they're really not suitable for servers just because they chose a different bandwidth to capacity ratio. They're more high bandwidth, low capacity. But for servers, we need something that has a better balance of that. Also, DDR in general is somewhat running out of gas. We need a step function in dollars per bit. As one of the Open Power projects is actually we use the Power high-speed serial memory interface, and we have a FPGA that you can use to innovate your own alternate memory models and still have direct memory access from the CPU. At the rack level, there's a lot of talk about disaggregated or versus highly integrated solutions. So there's advantages and disadvantages of each. As interconnect becomes less expensive, disaggregated becomes more possible, and a lot of talk about silicon photonics saving the day on that. Also with disaggregated I/O, you can have shared resource pools and better allocate your resources, get better utilizations. The downside is now with disaggregated, you might have a tightly coupled solution, so it may stifle innovation in terms of other partners connecting into your tightly coupled disaggregated solution. Also, you just have a latency problem. Speed of light, things move away from your compute, more latency you might get. Also, at the rack level, there's rack level solutions such as instead of alternatives to Ethernet, PCI switch networks or whatever. So I think that's an important innovation area that's coming as well. And that's it.
Next, I would like to invite Microsoft, Mark Shaw, if you could join us up here. He's going to give us a perspective from the end user.
Thank you. I'm happy to be here today as the only consumer of all this great technology that you see represented up here. Or perhaps in the future, because this is about roadmaps. So what Microsoft has found in our experiences of building clouds, clouds massive scale of servers and data centers, and and a huge number of widely varying services, is that consistency in the platforms, interoperability is paramount to keeping these infrastructures up and running. And so, you know, one of the things that we decided to do was we decided to start releasing our designs to the industry, taking our innovations that we get, push it out to the industry to get openness, innovation, interoperability, so that, you know, so that we can start building, you know, on the entire industry, you know, get these common platforms and start making it so that it's easier to actually innovate on what's really important. So, you know, I'm fond of saying inside of, you know, inside of the teams that, you know, our customers, people who are out there using Bing and Hotmail, it's not Hotmail, Outlook.com, they don't see value in a power supply. You know, what they see value is in a service that we provide. And so the infrastructure, you know, should be standardized, it should be simple, you know, the value needs to come in. What's in the silicon, what's in the software on top, and the services that are running. So we've gone to Open Compute Project and released our system. So last January we released the what we call the V1 systems. And just 2 weeks ago in OCP Europe, we announced our V2 systems. That's the latest blade upgrade. You know, basically a minor upgrade to the chassis and the major upgrade to the processor blades installed. And you know, what's really interesting about the consistency is that, you know, whereas we once had, you know, N number of vendors in our data center, all with their own different management and service models and that sort of thing, we now have one service model, one infrastructure. We actually had 5 different vendors on display with blades that all interoperate in one chassis. That's relative, you know, I think that's nearly unprecedented. Maybe back to the old VME chassis, maybe, you know, back in the 70s. Maybe that was the case back then, but, you know, modern days, you know, the machines just don't mix. Here they mix. And so, you know, we've decided to also do additional innovations. You know, like one of the things that we have is low-cost storage. So what we find is flash storage has turned out to be, you know, should have had this one before. Flash storage has turned out to be an amazing thing, you know. Especially in the cloud, you know, we use it for caching all over the place. A little stick like this is a ½ terabyte of flash. So it's an M.2 module. These M.2s, you have SATA-based versions in probably half the laptops that are out there now. You know, PCI Express NVMe high performance is coming, you know, coming soon. It's going to take over that industry, and you know, the M.2s we find, you know, great advantage for pulling that technology, you know, that's really born from clients, born from laptops, and pulling that into the cloud. And you know, along with standardization, you know, when we went off to initially design this system, you know, we said, well, what should we do? Should we build our own custom rack? You know, because there's a lot of space there wasted. We can get efficiencies in volume and that sort of thing. And what we ended up doing was going back to the 19-inch rack standard, which has its roots in the 1800s for train, let's see, along train tracks, you know, relay switches and things like that. It's an old standard, it's been around, it works for everybody. And, you know, that's just all part of this standardization. How do we make it simple to deploy hardware? Talking more about the flash, this is, you know, we're really excited about this, about these little modules. So when you look at you know, client to enterprise to cloud, you know, we've been working for years on this. We first went off and we said, well, what are our real requirements? You know, and one of the things that really stood out was the data retention. You know, 1 year. Well, basically, when we pull a server out, you know, a lot of our teams say, well, after, you know, if you have that machine powered off after 20 minutes, it's trash. You know, we're going to have to rebuild, you know, completely wipe the machine and rebuild it. So, you know, we don't need those types of data retentions. And so, you know, about 1 month is about right. But what we do need is a good level of endurance. You know, we don't need the best of endurance because we can use software to manage our machines and manage our endurance, manage the flash drives. We need a mid-level, and so as the nanometers keep shrinking and the raw endurance of flash devices keeps going downhill, we really have found value in, you know, controlling, you know, having the controllers, the software written so that we can actually get, you know, 20,000 writes, you know, of endurance out of these devices, and it's hugely beneficial. Another thing that we've been opening up, you'll see our research team has built an accelerator card out of FPGAs. So this accelerator card has 8 gigs of memory, a very nice FPGA with plenty of performance on it. PCIe, you know, Gen 3 interface, and a 2D Taurus network. So basically, we built our own out-of-band network for very low latency, high performance applications. And so you know, you can see that out on the data center floor, or the exhibit floor. So the contributions that we've been putting out, you know, trying to open up our hardware to the industry is pretty expansive. So, you know, again, we have the Open Cloud Server. That's the Open Compute. We release those specifications. You know, the chassis. You know, we're opening up, you know, Gerbers, mechanicals, all sorts of things about that. You know, some of our research projects, you know, that you're seeing, you know, not only are they delivering papers, but, you know, going around and letting people come have access, look at that, and the M.2 flash modules, which are so important to the systems. And that's it for now. So, thank you.
Next, I would like to invite Gaurav from the Applied Micro. As you know, Applied Micro is the first vendor that has their silicon based on ARM out there.
It doesn't help when everybody names their files the same. It might be the wrong one. Sorry. All right, thanks, Sergius, and it's a pleasure to be here again. I remember being here last year on the same stage, and what a difference a year makes, right? So far, we've always been talking about ARM in the servers in the future tense, right? But I'm really glad to say that for the first time, we actually have ARM servers that are ready to buy. So you can actually go out and buy ARM servers. It's really heartening to note that Intel is now talking about disrupting the data center. So it's a long time coming, and it just goes to show what a little bit of competition can do. So since this is a session on roadmaps, I thought I would start off with our roadmap. So the first ARM 64-bit CPU-based server SoC, which is XGene-1, which is our 40-nanometer SoC, is now shipping. That is the 4-channel memory with the DDR3 1600. XGene-2 is sampling, and XGene-3 is in design right now. We will have silicon by next year. What we also announced at TechCon a few weeks back was our embedded product line. And although I know this session is not about embedded products, but I thought I'd just put it out there. XGene is our server product line, and Helix is what we announced at TechCon. That is our embedded product line, and that is really targeted towards the communications, networking, imaging. And what's really interesting there is that we're bringing 64-bit, multi-core, multi-gigahertz ARM technology down to the sub 10 watts. So you can actually buy a chip that is, got 10 gigabit interface SoC for less than 10 watts, right? So you think of fanless applications and what that can do there. So we are very excited about that as well. So moving on, I mentioned the servers that are available, and right on top you'll see the HP ProLiant M400. This is the moonshot server that HP announced earlier at TechCon a few weeks back. And what's really interesting about that design is that people tend to talk about microservers, and well, you can call it a microserver because maybe it fits a lot of compute in a small form factor. But what it really is that it is very good compute with lots of memory and very fat I/O, all in a single cartridge. So it's actually very interesting if you think about it. If you think about the density that can bring in a 4U chassis, you can have 45 multi-core ARM processors. And that's only possible because of the low power, right, and the integration. It allows you to fit that mechanically into the small form factor. So we're very excited about the HP ProLiant. On the left, you'll see the MyTAC high density. That's a typical 1U pizza box chassis, which has 8 processors, XG processors in it. At the bottom on the left is the Dell box, and that's the Dell storage box. And what's interesting about that is that it uses a single XG, but it can be targeted towards the cold storage, but can also be targeted towards the Hadoop type applications. And the only reason that is possible is because cold storage doesn't really require that much performance. But what Dell found was that with XG, they had enough spare performance that they could actually target it towards the Hadoop type applications as well, where you really need to have very good performance. And I sort of agree with the comment made by the earlier comment that the speaker that wimpy cores don't cut it, so you really need to have good single-threaded performance. And part of the reason is that we were able to take a very good architecture, and I'm a CPU architect, worked all my life designing CPUs. So to Jeff's point, that the ARM 64-bit architecture is a very contemporaneous architecture, and it allowed Applied Micro to make a very high performance but still low power implementation of that architecture. And that's in those designs. The other 3 are HPC-based designs. And this is again very interesting because we never really started off trying to get into HPC, but we're seeing a lot of traction, and all those 3 boxes are for HPC. What people are doing is taking the CUDA platform, so we've got CUDA 6.0 ported over onto XGene, onto ARM64. And what they're finding out is that XGene with a GPU from NVIDIA gives identical performance with a Xeon E5 with an NVIDIA, right? Now, you can probably guess why, but the real reason is there is actually a significant amount of integer compute that is required in the HPC space, and XGene is able to deliver. So they can see a significant reduction in the cost and in the power, but still see the same performance. And that's the reason why there's lots of systems that are being designed for the HPC space. Another performance data, we get asked a lot about our performance and how we compare against the competition. So this is a live demo that we showed at TechCon. Again, this is a very apples-to-apples comparisons between multiple half-width servers with similar power. And this is running on an industry standard Nginx web server, and this is showing you the requests per second. And as you can see, that our current generation XGene 1 has better performance than the latest Haswell. But what's actually more interesting to me is that it comes at a much significantly lower latency. And as you know, in the web scale, it's all about latency, right? So this comes at all close to half the latency. Moving on, a few more of our customer experiences. On the upper left, you'll see this data that was published by Sandia. And it's actually interesting for me because I was responsible for the architecture for XGene, but it was my team that did the design for the memory subsystem. And I personally remember sitting through lots of these reviews where we tried to make sure that as the performance, as the number of processors scaled, each of those processors wasn't really starved for memory or cache bandwidth or the bandwidth of the interconnect. And it's good to see that because that really is the validation from the customer, because if you see the blue line, it shows you very close to linear performance improvement as you add more cores to it, right? And that really, again, goes to show that it's not just the CPU design, but it's also the interconnect, it's the memory subsystem architecture that we design ourselves. The one at the bottom is from CERN, and CERN, I was there. It's actually quite humbling when you go to CERN because the numbers are so staggering. They take 45 million pictures per second of these at the Hadron Collider. And they've got petabytes of data that they store. But this is running some of their applications, and it's interesting here, they've taken a well-tuned application that was running on x86, and they've compared that with an untuned application that they just very recently ported over onto ARM64. And as you can see that we are very, very comparable with the E5s. So this is again a good validation for us. In the interest of time, just move on really quickly. This is the M400 per line cartridge. People talk about TCO, and this is a white paper that was written where the HP per line M400 can offer 34% better or lower TCO compared to a system. And if you read the paper, it's actually very intelligently written. They're taking the E3 and the E5 product-based processors and comparing that with what you can do with an M400. It was interesting to see the Microsoft presentation, not this one, but the earlier one, where Microsoft announced that they also have Rocky. We saw this, in fact, 2 years back when we were looking at what to do beyond the processors. We've incorporated Rocky into XGene 2. So XGene 2 has native support for Rocky, and we see some really impressive performance improvements. And the reason is obvious, because you can take TCP latencies from, say, 50 microseconds down to Rocky latencies of 5 microseconds. And the reason is because Rocky does a lot of things in hardware. There aren't any buffer copies from when you go from kernel space to user space. It's a much more efficient system. And we hope that gets adopted. So it was very encouraging to see that Microsoft is looking beyond, but was also adopting Rocky. So that's my slide. So, I'm really glad to be here. And we have XGene 1 in production, XGene 2 sampling, XGene 3 around the corner. So if any of you were in doubt about ARM servers being real, well, it's here. I would highly encourage you to give it a try, and you might be pleasantly surprised at what you might find.
Thank you. And last but not least, we're going to be hearing from AMD. We start out with Intel versus the ARM, and now we're going to have a world of ambidextrous, which is can we all live together? With that,
all right. Thanks very much. Yeah, can't we all just get along? Right? I mean, that's really what it's about. Yeah, so this is, I think, the third or fourth time I've been to this conference. Previously, I was with a little company called Calzada, where we were all about ARM servers, and of course, we ran out of money before we could tape out our 64-bit chip. So now, after trying to sell ARM servers to the industry for 4 years, I finally have a 64-bit chip. It's great. We've shipped several hundred of these out to software developers around the world, and to really good response. People are excited about it. And next year is going to be a real turning point for ARM because we'll have our friends at Applied, they've got their chip out, we've got our 28 nanometer chip, and there'll be others as well, Cavium and others will be bringing this out. So what this means is a lot of choice. The good news is you're going to have a lot of choice. The bad news is you're going to have to choose. Right, so how do you choose? How do you choose between an ARM chip versus an x86 chip, or even other types? For us, it's a matter of focusing on the right workloads. And I think there's been a lot of talk about workload optimization. And what we're doing is taking that optimization down to the silicon. If what you're doing is traditional IT, running Windows or running Linux in your data center, we've got an x86 product line today. We've got another one coming out soon. We'll talk about that in just a minute. But for many of the cloudscape data centers, ARM is perhaps more appropriate for some of the workloads. Why? Because we can take innovative I/O and networking and put that together with standard ARM cores or custom ARM cores and be able to deliver a lot of value. Okay? And given a lot of value means a lot of innovation as as these building blocks can be combined in new ways. So you see a lot of choice again. But for AMD, we bring another, kind of a third leg in the stool, and that is acceleration. Your kids probably have AMD products in the living room. They're called game consoles, right? If you ever been to Las Vegas, you've probably seen an AMD product as well, which is we pretty much own the slot machine market, right? That's all graphics intensive processors that use x86 and graphics on a single die. It's very power efficient, it's very, very fast, it's very, very low cost. So gaming consoles, embedded applications, you can see us in, we have 95%, I believe, roughly, of the thin client market. So what you're seeing is technologies that can be optimized for specific workloads, and then the question is, well, are they good for the data center? Well, it turns out they can be. They can be, and this is what we call our APUs, and applying APUs into servers. So if you look at this slide, unfortunately, the most interesting part of the slide is in the left, which is the specific workloads. But what we have is we have a x86 CPUs today. There's some interesting announcements about some fantastic things people are doing with these at supercomputing next week in New Orleans. We've got our Seattle-based ARM server, which is again sampling today as a software development platform, and then it'll be focused on things like distributed object storage. It'll be focused on things like media servers, media streaming. It'll be focused on things like Hadoop and Cassandra and other big data constructs. And then we have our APUs. Today, you'll find that in the HP Moonshot. So primarily for hosted desktop infrastructure and things like that, the HP Moonshot is using the AMD Kyoto processor. We have new ones coming out that are really about bringing HSA to the market. HSA is the heterogeneous system architecture, which gives you a cache-coherent access to full main memory from the GPU on the same die as the x86 processor. So very low latency. You can eliminate the data copying from the CPU to the GPU, which saves a ton of performance, latency, and of course cost, and very, very high performance. Where's all this going in the future? Well, it's going to all get better. We haven't disclosed the details of the roadmap. Suffice it to say that everything on the right is 14 nanometer FinFET technology. We'll have next generation x86. We'll start talking about that probably in the middle of next year. Next generation ARM. These are also custom cores for ARM, and what they are called is Project Skybridge. What this means is a single socket that can accept both x86 and ARM. And so system designers will be able to design for a board with lots of memory and lots of I/O and lots of networking, and you'll be able to plug in an ARM chip or an x86 chip into that same socket. And that way, we can help lower the cost, lower the design costs, and speed time to market. The one on the lower right is the next generation server APU. This will really crank it up to 11. That's really a high performance computing chip. And again, we haven't disclosed anything about that yet, but all three of these in active development today, and we have non-disclosure discussions with end users and OEMs around the world, getting people pretty excited about this roadmap. So thank you very much.
Thank you, Bob. With that, we open up the floor for questions. Go ahead, please.
I want to liven things up a little bit. I almost fell asleep through some of the presentation. Everybody except Mark has a competitor right there. So my question is, if you look across just the competitors on the panel, who do you feel is your biggest competitor, biggest threat, and why? Okay, so that's for everybody except Mark. But I can't leave Mark a little more, so I got to kind of cover it too. So your OCS stuff is all based on Intel processors, right, Mark?
Today, yeah.
Today, yes. So if you look at the other options, you got a few ARM options, you've got AMD x86, they do x86 still. And you've got power. So with all these other choices, who do you think is most likely to win your business and why?
So one of the things that we did with OCS was we made it, if you look at the specs, yes, the specs call out the Intel processors, but the specs are really about the volumes, the boundaries, the chassis, the infrastructure, the management. That crosses all instruction set boundaries. It doesn't matter who's, anyone can build a blade and put it in there. And it's about the software that runs on top of it. And so, so this is one of the beauties of the system that we're trying to build, is that, as these different systems come to market, come to bear, as we build these things up, we can just plug them in and try them out. It's like, why not?
That means you have a shot at it as well. Everybody's included there. Any other questions?
The other panelists need to answer the question.
Okay.
And maybe not allowed to say none of the above.
Okay.
All right, maybe you can get started. So, it's an interesting question. I think for Applied Micro, since we happen to be the first out with a alternative processor, and I think in my mind, there's only one person who has the market today, pretty much, right? So that's pretty obvious as to who the competition there is. But I think to me, it's really about. From the first ARM guys, is to oftentimes the competition is ourselves, because people are looking to us to really deliver value, right? To deliver something that's really beneficial in some way, right? So to that regard, really what the ARM V8 architecture has done is really open the floodgates for us to innovate. So in that sense, it's really up to us to demonstrate the value, and I think that good things will happen.
So I think I'll take a similar tack. I think the biggest competition is resistance to change. Okay, and that's true whether it's AMD trying to sell a different x86 or an ARM or an right? And the way you overcome change is by delivering substantial value. Nobody's going to adopt an APU and go through the pain of OpenCL or HSA or anything else if it doesn't deliver significant value. That's why we're doing it, is focused on very, very specific workloads where we can deliver 10 times better performance, right? And so that's really the challenge I think that we're all faced with, whether it's power, x86, APUs, or ARM, is delivering that, overcoming that change. I mean, there's no question, who do we compete with? Well, I don't compete with Applied. Anybody that is confused about whether they buy an Applied chip or Seattle's hasn't read the spec. These are very different parts. And power, that's a completely different. I mean, that thing, Power 8 is a beast. It's amazing, an amazing technology. No one's ever going to get confused about buying that or an AMD chip. It's a very different cost point, very different power envelope, very different performance characteristics.
One last comment, since we have to close. Any other comments?
Well, I think it's clear who has the market share, and Open Power is trying to get a piece of that pie. So it's clear. This is the server class power, not the embedded power. It's Power 8. Yeah, Power 8 is the current product.
Yeah, I think from my perspective, as Carl said, the biggest competition is probably change and legacy. But then a lot of the discussions we've seen here this week revolve around the fact that scale out is happening. There's different ways to do things. A lot of this stuff is powered by open source, so legacy barriers that were historic have largely been torn down. From a market share standpoint, clearly, we know who has the market share there. Having one vendor with such a large market share is not really a healthy position. Fundamentally, we believe that as workloads are diverse and people should have more workload optimized solutions, you're going to need a broader spectrum of solutions to choose from. That's what the ARM ecosystem, that's what the power guys are doing. We're bringing that choice and innovation to a market that's been, I guess, largely devoid of it for a large time. So it's going to be an interesting couple of years.
So the question was if I'm afraid of anybody on the panel per se. I would say that if I look at it right now, like 2015 would be definitely a year where we figure out where competition is. Being a computer architect myself before, I understand the value that Intel brings to the table. We're not afraid of change. We've talked about this before. We've tried very hard to stay on top of the emerging workloads. Any given day, there are 13 to 16 ARM licenses. There's compute coming up from the IBM side of things. I think collectively, yes, there is competition out there. I wouldn't say that there is one particular competition that I would point to say. And it's not necessarily people sitting on this panel. There are other people who have not participated on the panel. So we're always looking out for who the competition would be. I would say 2015 will dictate where things actually go.
With that said, thank you everybody for attending. Have a great evening.
Friendly.